Okay, now let's recommend an asset allocation using mean variance optimization. Recommend which of the following 3 strategic asset allocations is appropriate for Marsha Bronston. Okay, so some of the facts. Her risk tolerance is average. So the lambda, that measure of risk aversion, is equal to 4. Like we said, it's generally on a range between 0 and 10, 0 being risk neutral, 10 being very risk averse. If her measure of lambda is a 4, she's sort of right in the middle there. She wants to minimize the chance of earning less than 3%. So when you hear a phrase like that, minimize the chance, minimize the probability of earning less than this, well then maybe we can start thinking about a safety first criterion there, right? That's what we're trying to address with that type of statement. All right, so let's say we have 3 allocations. Expected returns of 8, 6, and 4% with the following variances. Now, notice that the expected returns are in percentage form, the variances are in decimal form. Okay, so when we go through these calculations, you probably want to make sure that you're doing everything in one term or the other, everything in percentages or everything in decimals, just to make sure that that doesn't trip you up. So that is something that's very common that they will do. They will throw numbers in both forms and basically expect you to understand how to read them and how to use them properly. Okay, so recommend which of the 3 strategic asset allocations is appropriate. Okay, so one way we could do this is by using a utility function. So we have a lambda, we have a risk aversion coefficient of 4. And so what we can do is then use our utility equation to figure out which one of these asset allocations give us the highest expected utility. Okay. Now notice the coefficient here in that second term is 0.5, not 0.005. So if it's listed as just 0.5, that means we need to put these numbers in here in decimal form. So 8% is going to be 0.08. The variance is going to be 0.0225. So we get a utility equal to 0.035, or if you want to think of that in percentage terms, that's 3.5%. All right, so we do the same thing with number 2, and we do the same thing with number 3. So each of their respective expected returns in that first term there, the coefficient is 0.5 in all 3 cases, the lambda is 4 in all 3 cases, and plug in the respective variances. So when we get done running through these utility functions, what do we find? We find that the allocation number 1 and allocation 3 both give us the same amount of utility. Well, number 2 drops out because it is the worst of the 3. Now, if I want to look at Roy's safety first criterion, right? One of her descriptions in wanting an optimized portfolio is to say that she wanted to minimize the probability that her return was below some sort of minimally accepted level or minimal acceptable level. So that's Roy's safety first criterion. So R sub L is going to be the minimum acceptable return. RP is the return of the portfolio. Sigma P is the standard deviation of the portfolio. So what does Roy's safety first criterion tell us? It's kind of like calculating a z-score, basically. We're taking our value minus the minimum acceptable return and dividing by the standard deviation. Remember, the standard deviation is the square root of the variance. We're given the variance, so we have to raise those to the 0.5 power. So if we do that for 1, 2, and 3, what do we get? We get values of those 2 portfolios. If we've already eliminated 2, well, maybe we can just focus on 1 and 3. But if we get values for Roy's safety first criterion, certainly number 1 appears to be the better choice. And so given those 2 criterion, if we already eliminated number 2, well, then we can use Roy's safety first criterion to say, yes, we want to choose number 1. Okay, another example, different facts. The risk-free rate is 3%. If the client and the manager believe a true risk-free asset exists and can be used to construct the strategic asset allocation, identify the appropriate asset allocation for Plowshare and calculate the risk of the optimal allocation. Here are the facts. Plowshare University's endowment's return objective is 9%, which covers the spending rate, inflation, and investment expenses. They seek to minimize standard deviation of return while meeting the return objective subject to a non-negativity constraint. What does that mean? It means we're not going to do any borrowing, we're not going to do any short selling. So all the weights are going to be 0 or positive. So let's look at our allocation choices. AA, BB, CC, D. Our relative expected returns there and standard deviation we can compare across those 4 groups. Okay, so that's our input data. So how do we decide which one is the best choice? Okay, so notice, first of all the returns exceed the required 9%. All right, so that's the good news, right? They want to earn at least 9%, so all 4 qualify in terms of that. No borrowing or a negative weight is needed. Okay, so we're assuming here that the weights that go into these allocation choices, all of them have weights greater than or equal to 0 in their respective asset classes within each allocation choice. And so what we want to do here, let's say we want to select the best Sharpe ratio. Okay, what's the Sharpe ratio? Remember, it is the portfolio return minus the risk-free rate divided by the standard deviation. So if I do that for AA, its expected return is 15. We specified the risk-free rate as being 3, divided by the standard deviation of 24, so we have a Sharpe ratio of 0.5. All right, so let's keep doing that for B, C, and D. So we're going to plug in their respective returns. In each case, 18 for double B, 12 for double C, and 10 for double D. Subtract out that risk-free rate, and then divide by that standard deviation, and that's going to give us the Sharpe ratio of these 4 portfolios. The Sharpe ratio tells us we want to choose the one that has the highest Sharpe ratio, right? It gives us the greatest amount of excess return per unit of risk. And so what's our choice there? It's going to be double B because its Sharpe ratio is 0.56. Okay, so if we're assuming that double B is our choice, our portfolio allocation of choice, okay? Now let's do some other things with this. What do we want to say is the allocation between double B, which let's say that's the risky portfolio, and the risk-free rate in order for them to earn the required 9%. Okay, so if they choose double B, yeah, double B has the highest Sharpe ratio. It also has an expected rate of return of 18%. If their target is 9%, well, then what we can do is to say, look, you can invest in double B, but we'll weight that with a risk-free asset so that we'll get you the return that you're looking for. But because we're combining this with a risk-free asset, then we can bring the portfolio standard deviation down significantly. So how do we figure out what the weights need to be to get to that 9%? It's just going to be a weighted average, basically, right? So we're going to say we want to target 9 on the left-hand side, and we figure out the weights, right? W and 1 minus W, because the weights have to add up to 1. So whatever W is, the other one has to be 1 minus W. And then solve for W. So if I have 18% expected return in the risky portfolio, 3% in the risk-free asset, we find out that a weight of 40% in double B and 60% of the risk-free rate will give us an expected return of exactly 9%. If you want to check the math on that, take 18% and multiply it by 0.4. That gets you 7.2%. Then add to that a 0.6 weight multiplied by 3. That gets you 1.8. 7.2 plus 1.8 gets you 9% exactly. Now, what's the standard deviation of this portfolio? Well, the risk-free asset we assume has a standard deviation of 0, so basically that term is going to drop out of the equation, and so the standard deviation of this portfolio is just going to be the 40% that we allocate to the risky portfolio, double B, multiplied by its standard deviation of 27, and that will be a standard deviation of 10.8%.